Good morning from Germany. My name is Claire Cobley, and I'm the editor-in-chief of ChemNanoMat. Thank you all for joining us today for some exciting talks from the inaugural members of our early career advisory board members at the journals affiliated with the Asian Chemical Editorial Society, also known as ACES. So I'm going to share a couple of quick slides. You here? Now, for those of you that haven't heard of ACES before, it is a collaboration between 12 different chemical societies from across Asia and the Pacific, and co-publishes 3 journals together with Wiley BCH: Chemistry and Asian Journal, the Asian Journal of Organic Chemistry, and ChemNanoMat. My colleague Andre Dragan, the deputy editor of the Asian Journal of Organic Chemistry, is also on with us today. For today's event, we have invited one early career advisory board member from each journal to speak about their research. We launched these boards at the start of the year in order to build stronger connections with earlier career researchers, and are looking forward to working with them in the months to come. Our moderator today is Professor Paul Plieger of Massey University. Paul joins us through his role with the New Zealand Institute of Chemistry, one of our ACES partner societies, and will be leading the question and answer session. So without further ado, I'm going to hand it over to you, Paul.
Thank you, Claire. So on behalf of the Asian Chemical Editorial Society and Wiley BCH, I wish to extend a warm welcome to all our participants today, and also you, our audience members, to this, the inaugural Asian Chemical Editorial Society Journals Early Career Advisory Board Virtual Symposium. We have 3 excellent speakers this evening, evening where I am, covering the 3 early career advisory boards across Chemistry, Asian Journal of Organic Chemistry, and ChemNanoMat. Each talk will be approximately 25 minutes long, after which point there will be some minutes for questions. Please, if you wish to ask a question, type it in the attendee chat as you think of it. That will just save some time. So don't wait to the end. Proceed also with your question with the @ symbol. So this will allow us to spot the question a little more easily. My apologies in advance if your question is not read out, as we will have limited time and we may not get to them all. The speakers may answer them in the chat themselves after they've given their talks. Okay, without further ado, let us begin. Our first speaker this evening is Assistant Professor Dr. Junzhi Liu. Dr. Liu obtained his PhD degree in synthetic chemistry at the beginning of 2016 from the Max-Planck Institute for Polymer Research under Professor Klaus Mullen. Postdoctoral studies at TU Dresden with Professor Feng was followed by a research group leadership position for molecular functional materials, also at TU Dresden. In August 2019, Dr. Liu started his group at the Department of Chemistry in the University of Hong Kong. Dr. Liu has won a number of international young career prizes, including the International Union for Pure and Applied Chemistry International Award for Young Chemists. And as Claire has already mentioned, Dr. Liu is an early career advisory board member for Chemistry and Asian Journal from this year. Dr. Liu will be speaking to us today on rational synthesis of defective nanographenes with non-alternate topology. Dr. Liu, when you are ready, thank you.
Great. Okay. First, I would like to thank you, the SAES team, to make this online event happen at this special time. It's my great pleasure to share my research work at here. And so today, my research work is about rational synthesis of defective nanographenes with non-alternate topology, such as with 5 or 7 membranes, or even multi-edge 7 and 5 membranes. I think maybe the audience are not come from this field, so I would like to introduce some general introduction about this field, such as graphene nanostructures, especially from the chemistry point of view. Actually, graphene nanostructures, which also called polycycle aromatic hydrocarbons, which back to the 100 years ago, which initiated by Schur and Clark. At that time, the representative pHs and chemical reactions are explored, and the basic chemical characterization are established, such as by using UV laser spectroscopy. And later on, the large, fully benzonide and closed-cell pHs are very developed in the last 20 to 30 years, especially from the contribution of Professor Klaus Mühlen, such as right now, he already achieved the largest nanographene, which contains 222 carbon atoms. The breakthrough in this field, he developed the synthetic strategies by the Schur reaction and since developed to different shapes and geometries. So later on, such as the last 10 years, we call the third generation, people are developed for the large system from the small molecular to polymers. We called it graphene nanoribbons. The first graphene nanoribbon was synthesized on the surface in 2010 with we call it 7A gene Rs. After that, different synthetic strategies for the gene Rs was developed by different people, such as Diels-Alder reaction, Suzuki polymerization, and Yamamoto polymerization. At the same time, instead of the solution synthesis, people also developed the on-surface synthesis, which people can will control the length and edge structure, such as from 7, 9, even 13 or 15 with graphene nanoribbons, or even different edges, such as curved edge or zigzag edges. That means people can will control the electronic band gap. At this moment, we think we are now at the fourth generation. We call it, we divided into different directions, such as the large non-calcular type graphene molecules with open shell radicals, and also concealed non-calcular graphene molecules. At this moment, people also developed the non-hexagonal rings containing nanographenes, such as with 5 and 7 member rings, also graphene nanoribbon with edge states, or heterojunction graphene nanoribbons. So today, I'm more focused on this non-hexagonal ring embedded nanographenes, such as with 5 and 7 member rings. Actually, when people mention the defects, there is a Chinese saying said like this: gold cannot be pure, man cannot be perfect. For example, the diamond. The perfect diamond is cubic crystals. The color should be colorless. However, normally you will see the yellow diamond or green diamond. Actually, the yellow diamond is due to the such as nitrogen atom doped in this cubic crystals. For the green diamond, there is due to the multi defects in this cubic crystals. That means defects can change the physical and optical purpose for the materials. Actually, we also see defects in our nature. Maybe you already noted that many pictures about the hexagons, such as the snowflakes, the honeycombs, or even the basalt columns. However, if you look carefully in this honeycombs, you can see there are some 5 and 7 member rings in this 6 member rings. We call it Azulene from the chemistry point of view. The similar, if you look at this basalt columns, you will see there are some 5 member rings fused together. From the chemistry point of view, we call it pentane. So it's quite interesting from nature, we also get some monoconers. Actually, there are also defects in the graphene. Maybe people already know that graphene also can be regarded as fused benzene with 6 member rings. But however, there are also some dislocation of these atoms, such as formation of these 5 and 7 member rings. And also, you can see in this figure, there are also 5 and 5 member rings fused together. We call it pentane, also 8 member rings. From the theoretical calculation, people found that these defects also can be open the band gap of graphene. For example, this 5033, we call it class 2 defects. The energy gap is about 1.10 EV compared to the 0 EV of this graphene. This is due to this defects can be the green boundary of graphene and the formation of this polycrystalline graphene and open the band gap of this graphene nanostructure. But however, there are also some challenges in these defects. For example, right now, most workers are focused on the theoretical characterization and also only about this simulation. And usually, the defects in graphene are uncontrolled. Therefore, the physical and chemical purpose of these topological defects in graphene, they are very poorly understood. So that it motivates us to control the defects, such as we are asking ourselves, is there possible to synthesize these defects in graphene nanostructure with automatic processes, such as by using bottom-up organic synthesis, in which the defects can be introduced selectivity and provide this insight into the structure-purpose relationship. Actually, bottom-up organic synthesis, as we mentioned before, is a powerful tool for the synthesis of large polycyclic aromatic hydrocarbons. However, despite this achieved progress in PAHs, they are most focused on the 6 member rings. The synthesis of different topological defects in graphene nanostructures, such as with 5 or 7 or even 8 member rings in graphene nanostructure, are largely unexploited due to the lack of facial synthetic method and due to the stability. So our focus is try to introduce this perfect defects into the graphene nanostructures to control the geometry and aromaticity, such as is it possible to synthesize anti-aromatic molecules or even pro-aromatic graphene molecules. For example, we can synthesis of this stable open shell biradical compounds with heptagons as permission spintronics. If you back to the history of 7 member rings, actually before the 2010, there are not too many examples to synthesis of this 7 member ring embedded molecules or nanographenes. After 2010, people are paying more attention to synthesis of this 7 member ring embedded nanographene. So we are thinking about is it possible to build 5 and 7 together, such as we introduced before, such as this is a tuning unit with 5 and 7 fused together. But based on our previous research, we can selectively formation this 5 member ring due to this 1-to-phenol migration during the Schur reaction, which can be pulled by the single crystal. So we are thinking about is it possible to build this 7 member ring by one more carbon atom, such as this kind of structure. We can build one more 7 member ring closely with 5 member ring. And we found that this kind of molecular have large biradical character by using the DFT calculation. And you can see this figure is about the spin density of this molecular. You can see the spin density is more localized on the cell membrane. Then this molecule turn on the first case of radicals on the cell membranes. So we designed the synthetic routes toward this kind of Azulene embedded nanographene, such as we can do the Suzuki coupling, and then iodine chloride induced cyclization, we can fuse this triple bond. After that, we have already developed this 1,2 phenol regulation. We can selectively formation this 5 membrane at first, and then we oxidize this methyl group to aldehyde. After that, we do the Fed-Craft reaction. We can close this ring with 7 membranes, and after that, we do the oxidation to dehydrogenation this proton to get this fully fused or fully conjugated molecular, which can be pulled by the single crystal structure. And compared to the only single membrane polycycle or aromatic carbons, which are mostly curved structure, this kind of 5-7 together embedded molecular possess planar structure. As mentioned before, this kind of molecular also have the biradical character, or we call it open shell kind of molecular. Then we further performed this molecular by EPR and screed. From the EPR measurement, you can see increase the temperature. The single also increased. This is due to the excited this singlet to the triplet species in this molecular. Furthermore, we also proved this behavior by the screed measurement, and by using this fitting, we can estimate this singlet triplet energy gap is about 2.5 calculate per mole. Furthermore, we also investigate the stability of this kind of molecular by using UV VISA. As you can see, after 16 minutes, after half an hour, the signal slowly decreased, and the half time of this kind of molecular is only 2 hours. It means the open shell molecular based on this same membrane is very unstable, and the optical energy gap of this molecular is about 1.1 eV. So due to this stability issue, we are thinking about to building the stable compound containing this 5 and 7 membranes. Very recently, we found that by this Schur reaction, actually this reaction is unexpected during this Schur reaction. First, we do the sugar coupling with this phenolene, and then follow this gather coupling, we can formation this dimer acetylene, and using this iodine chloride to fuse this triple bond, we can get this diiodine compound. Actually, at the beginning, we try to use this diiodine compound 8 to get this compound 9. We call it heptene, in which there are 2 7 membrane fused together. However, we failed when we do the Schur reaction, and we unexpectedly give this 5-7 membrane fused embedded nanographene, and turned out this honeycomb nanographene containing this Azulene embedded nanographene, which can be confirmed by the single crystal structure, in which we can clearly see this 5 and 7 membrane inside. However, compared to this pure 6-member ring embedded nanographene or halogens. This kind of molecular display different behaviors, such as they have different angles and different packing. From the certain state, you can see the packing of this kind of molecular have large pi distance is about 3.8 angstrom. Moreover, we also calculate the aromaticity of this kind of molecular. As you can see, the 7-member ring become non-aromatic, or we call it anti-aromatic about this 7-member rings compared to this aromatic 6-member rings, and this 5-member ring become non-aromatic. This figure is about the SID, about the ring current on this molecular. As you can see clearly, this 5 and 7 ring become more paramagnetic. However, this outside the 6-member ring still displays the diamagnetic. And finally, this kind of compound shows a group aromaticity feature. Moreover, because this reaction were discovered unexpectedly, so we think this maybe can be generally used for synthesis of large or helical nanographene containing Azulene unit. So we designed more large systems, such as we using there's other reaction, use this CP to build this diacetylene compounds. After that, we follow the similar synthetic routes, such as by using iodine chloride to fuse this triple bond to get this diiodine compound. Then, following the same short reaction, interestingly, we can achieve this large pi system Azulene embedded helical graphene nanostructure compared to our previous case. Interestingly, when we did this short reaction, we found that this iodine maybe can still live at here as a functional group to achieve these two different kind of molecular as a one-port reaction, which also can be clearly confirmed by the single crystal structures. As you can see, this 6 halogen containing 5 and 7 membranes also twist this molecular out of this planarity formation, this helical structure. Moreover, we also did the DFT calculation. We found that this embedded 7 and 5 membranes is also display paramagnetic purpose compared to the outer 6 membranes performs diamagnetic. And this two kind of molecular is also can be considered as global aromaticity molecular. So, moreover, instead of this pure 5 or 6 membranes, we also try to tighten the electric structure by using hydrogen atoms, such as we can introduce this NBN unit into this 5 and 6 membranes. So this is a synthetic route in which very important I should mention that we can use this TMS group as the leading group in which we can formation this NBN unit. After that, we can do the Higg and Yamamoto reaction to formation this 5 and 7 membranes. Finally, we also can be confirm this structure by using single crystal. As you can see clearly, this 5 membrane turned out more planar structure. However, this 7 membrane will induce this molecule out of this planarity. And from the crystal packing, you can see this planar 5-member ring embedded molecular have a very beautiful packing. Its formation this Harry-Bound crystal packing. It motivates us maybe this kind of molecule can be useful for the transistor. So furthermore, we did the single crystal OFAT for this two kind of molecular. We found that indeed this kind of planar structure performed much higher mobility compared to this non-planar structure due to this less pi staking. As I mentioned before, we synthesize this kind of 5 and 7 member ring nanographene in the solution. Actually, we also can synthesize of this non-hexagonal rings on the surface. So furthermore, we combine this solution-based synthesis and on-surface synthesis to build more large systems, such as in the solution, we can synthesize of this this kind of compound 1 with bromine as a functional group. Then we deposit this compound 1 on the surface. Then they will generate the dimer on the surface. After that, we do the oxidative ring closure. Then this methyl group will formation this additional 7-member rings. Finally, they will formation this 5 and 7-member ring together compound. Then further, we can increase the temperature to do the cyclodehydrogenation between this 6-member ring. And finally, we can achieve this two kind of molecular. We call it 2A and 2B. Very interestingly, at this reaction, we found that this six-member ring will go the ring rearrangement to formation this pentane structure. As you can see, two 5-member ring fused together. And for the other one, the 6-member ring also will go the ring rearrangement to forming this induction unit embedded in this graph nanostructure. Furthermore, this kind of structure was further confirmed by the STM and the AFM measurement. As you can see from the AFM measurement, it's clearly to see that this same membrane formation at the atomic level. And also this is the pentane unit from the FM. And we also calculate this geometry structure on the DFT, which is very agreement of the experimental. And furthermore, we can check the electronic band gap of this two kind of molecular by using STS measurement. As you can see, for the 2A, the energy gap is about 0.96 EV. However, the 2B, the electronic structure is about 0.85 EV. So from this experimental results, we are thinking about this two kind of molecular maybe behave the open shell feature. Furthermore, we did the DFT calculation. Indeed, we found that the bi-radical character of 2A is about 61%. However, 2B, the bi-radical character is about 33%. It means due to the different geometry, these two kind of molecular featured different bi-radical character. 2A is much higher than 2B. Furthermore, we also did the spin density calculation for the 2A and 2B. As you can see in this figure, they also display different spin density behavior around on this molecular. As you can see, for the 2A, the spin density are more localized on these two cell membrane. These two cell membrane are two different sides. However, for the 2B, the spin density are localized on one side. So it means we can control. It means due to the different geometry, we can control the electronic behavior for different molecules. So, summary for our work. Actually, if you go back to the history of the cell membrane, actually, before 2010, people are more focused on this small molecule only containing cell membranes. However, due to the last decades from the 2010, people are more focused on this 5 and 7 membrane. However, most is 5 and 7, they are separated. So due to the last 2 years, I think people are more focused on the 5, 7 membrane, which are fused together. We call it Azulene unit, such as we also developed several kind of molecular, especially in this year, 2020, people get more and more attention for this field, such as there are more than 4 molecular have been synthesized, have been achieved from different groups. So I think maybe in the next 5 years, this 5 cell membrane maybe can be a hot topic in this field. So outlook, as I mentioned before, the cell membrane embedded nanographene with open cell biradicals, they are very, very unstable, such as we demonstrated that this kind of molecular, the half-time is about 2 hours. Later on, Cornish group, they also synthesized this haptene embedded nanographene with biradicals. However, the half-time is only 3 hours. So we are thinking about, is there possible to synthesize this stable molecules with heptagons? So very recently, it's true that we can achieve this high stable biradicals containing cell membranes. For example, from the zerotic calculation, the biradical is about 0.3. However, this kind of molecular also featured with large singlet triplet energy scale. That's why this kind of molecular is very stable. We can confirm this structure by single crystal. Hopefully, I can tell you more details in the future. So at last, I would thank my previous mentors, Professor Klaus Müller and Professor Xinliang Feng, and also my partners. If there is no contribution from their side, I cannot achieve such kind of molecules, especially from the Professor Roman Father for the surface synthesis and David Beju for the zerotic calculation. And also my group from the TU Dresden and also right now from the HKU. So thank you all for your kind attention and welcome to Hong Kong. Thank you very much.
Thank you, Dr. Liu. Thank you very much. Very good talk. I'm just looking in the chat. It looks like we don't have too many questions at this stage. I have a couple of those. So for your compounds that you had in your talk, I think compounds 8 and also for that matter 2 and 3, the ones that had the P and M isomers. I was wondering, yes. I was wondering if you'd had a look at the activation of rotation. Is it possible to interconvert between the P and M isomers for those systems?
You mean separate these isomers?
Well, I mean, you can separate them as isomers, but then can you actually take, for instance, the P isomer and heat it up and get an equilibrium? Like, is the activation barrier within reach? Or are they too?
I see. And next question. We didn't try, but it might be possible, such as we can deposit this P or M isomers on the surface and then heating it to see there is some isomer transformation due to heating or something. But it's quite interesting. Maybe we can try in the future. Good question. Good. Yes. Maybe maybe it's worth to try. Nice question. Mm-hmm.
Thank you. And a lot of it also, these types of systems suffer usually from solubility issues. I notice you've had a lot of butyl groups on them and things. So do you have problems with solubility with these systems?
Yes, actually, for all the large pi systems or large polycycle or aromatic hydrocarbons that meet the solubility, especially in the solution synthesis. That's why normally we introduce some bucket group at the edge of this molecules to improve the solubility for the synthesis. Yes, we meet the problem. But however, if we introduce some large arc chains or something, it will influence the packing. It means if you want to do device, maybe the performance will decrease or some other effect.
All right. Thank you very much.
Thank you.
Yes, and we'll move forward. Thank you for your talk.
Mm-hmm.
Okay, so our second speaker this evening is Associate Professor Youhei Takeda. So Dr. Takeda obtained his PhD in material chemistry in 2010 from Kyoto University under Professor Hayama. Postdoctoral studies at MIT with Professor Swaga was followed by an assistant professorship at Osaka University in 2011. And Dr. Takeda then became associate professor in 2015 and also holds a number of adjunct positions. Dr. Takeda has also won the Young Scientist Prize, which is accommodation for science and technology by the Minister of Education, Culture, Sports, Science and Technology in Japan. That was won this year, and also a Young Scholar Lectureship from the Chemistry Society of Japan, also earlier this year at their 100th annual meeting. Dr. Takeda is on the Early Career Advisory Board for the Asian Journal of Organic Chemistry as of this year, and will be speaking to us today on the development of photofunctional organic materials, lessons from new reactions, and scaffolds. Dr. Takeda, if you are ready, please begin your talk. Thank you.
Thank you, Paul. Can you hear me? Okay.
Yes, we can.
Okay. So first of all, I'd like to thank Claire and Andre and congratulations on this memorable virtual event. So I would like to thank Claire and Andre, also all the ACES committee members for providing me with a great opportunities to give a talk about our research. So I'm Youhei Takeda of Osaka University, Japan. So I just became an early career advisory board member for Asian Journal of Organic Chemistry, starting from this January. So far, I'm very happy working with the editorial team. So I'm an organic chemist, and what we have mainly focused on over the several years encompasses interdisciplinary researches. Interdisciplinary research is aimed at the development of multi-photofunctional organic materials driven by the discovery of new reactions and scaffolds as shown in this title. So we believe that even small discoveries such as finding new reactions and molecular scaffolds will bring us a significant breakthrough in material sciences.
Dr. Takeda, sorry, we cannot see your slides. Are you sharing your skits?
Oh, really? Sorry. Can't see this?
Not at this stage. We're just going to try and find out why not. Just bear with us for 1 minute.
Okay. Can I try it once again?
Okay, so we can see you. Just need to, oh, yeah, that's. Yes, that's it.
Okay, now you can see this, right?
Yes.
Okay, thank you. Sorry. So here is the overview of my presentation. Okay. So as you know, the pi-conjugated organic compounds structure is diverse, and many people are fascinated simply by the geometrical beauty of pi-conjugated compounds. Also, we recognize a lot of challenges in the synthesis of the artificial beautiful molecules, or like these molecules. So what is more, due to the existence of pi electrons delocalized through molecules, pi conjugated organic molecules display photon and electron functions. So they can find many applications in the displays, solar cells, lightings, and bioimaging. Of many types of pi electron conjugated systems, we are interested in other analogs of the polycyclic aromatic hydrocarbons that is often dubbed as PAHs. So the replacement of the carbon atoms of PAHs with nitrogen atoms in the other molecules or with some unique physical-chemical properties as organic function materials, such as increased electron affinities, large dipole moments, and versatile character, and the unique packing structures in the solid state. So the story about the first industrial organic dyes discovered by Professor Sir William Parkin provided me an inspiration. So to make a long story short, he happened to discover the production of the isomeric or mixture of phenazine salts in the oxidation of aniline derivatives in attempting to synthesize quinine. So this story tells us a good lesson that the oxidation of aromatic amines should be useful for constructing functional aza-PAHs. Yes, it is, but we often struggle with over-oxidation of the aromatic amines. So regardless of its high potency as synthetic tools, the regulation of the oxidation of aromatic amines remains a big challenge in organic synthesis and material sciences. So by regulating the oxidative process of aromatic amines, we successfully developed a variety of oxidative transformations of aromatic amines into functional aza-containing pi-conjugated compounds over the several years. So due to the lack of time, today I'm going to introduce only one example that allowed for developing much functional organic materials, as shown here. So in 2012, one of my PhD students found out that treatment of binaphthalene or diamine with an iodine-containing oxidant resulted in unexpected formation of a U-shaped or diazo-azane compound shown here. So we are very surprised as a result because the discovered rearrangement reaction formally involves the cleavage of the very strong CC single bond here and the migration of the nitrogen atom into the adjacent position. So since the U-shaped compound is otherwise difficult to synthesize by conventional organic reactions, intuitively, I felt sure this reaction would bring a breakthrough in my research. Under the optimized conditions, U-shaped diazo-azanes are available in moderate to good yield. So through the optimization studies on the reaction conditions, we found the oxidant, or DRH shown here, gave dibenzophenolene selectively in a high yield, while tertiary butyl hypochlorite, or exclusively avoided diazo 5-hexane here. It is worth mentioning that the production of these unique structural or constitutional isomers is totally switched just by changing the element of an electrophilic oxidant. The optimized reaction conditions allow for the synthesis of a variety of U-shaped diazoxanes here in good to high yield. Specifically, it is important that the synthetic method is applicable to the synthesis of dibenzophenolene having two dibrom of functionalities here, which is readily converted into extra functionality and extended pi system by transition metal catalysis. So from the viewpoint of functions, dibenzophenolanes are emissive in both solution and solid state, and they also serve as good electron acceptor comparable to Al2,3, which is a well-known electron transporting material. So we decided to develop more unique organic luminophores by making use of the characteristics of the U-shaped diazoxanes. So we designed a thermally activated delayed fluorescence TADF emitters for OLED devices utilizing U-shaped diazoxanes as the electron accepting core. So this twisted donor acceptor systems effectively generate intermolecular charge transfer excited state, or CT1, whose photophysical properties are tunable just by fluctuating parameters such as electronic biases and donor acceptor dihedral angles here to adjust a single triplet energy gap suitable for efficient reverse system crossing. So, as you may know, according to the spin statics rule, the electronic excitation of a luminophore in an emissive layer always generates singlet and triplet excitons in 1:3 ratio. Because of the ratio, as long as we utilize conventional fluorescent compound, which is dubbed as the first generation fluorescent emitters, as the emitters, external quantum efficiencies of OLED does not exceed the theoretical maximum of 5%. So the bottleneck here to increase the efficiency of OLED is how to efficiently harvest the triplet excitons and convert it into light. So basically, there are three approaches for this purpose as shown here. Out of them, the two approaches can technically harvest 100% excitons generated by the electron. The first option is to utilize room temperature phosphorescence materials based on heavy metal complexes such as iridium and platinum. So, however, they contain non-sustainable layer metals such as iridium and platinum. The second one is the utilization of thermally activated delayed fluorescence materials, where reverse intersystem crossing from the triplet excited state to the singlet excited state is enabled by very small single or triplet energy gap. So indeed, the last several years have witnessed a significant advancement in TADF research because comparable quantum efficiencies with those using phosphorescence materials are achievable with purely organic molecules comprising of commonly available elements such as carbon, hydrogen, and nitrogen. Although there are many types of materials or design reported, a simple way to yield purely organic TADF is connecting the suitable donor and acceptor unit and twisting these. Since the delta EST between the singlet and the triplet is proportional to the electron exchange energy of the unpaired two electrons in the excited state, a simplified blueprint for minimizing this to accelerate the risk process is decoupling the HOMO and the LUMO of a molecule. So recently, there are a lot of design strategies that are proposed and invented. So to investigate the effect of donors on TADF properties, a variety of TAD compounds were designed and synthesized through the paradigm catalyst Hardwick backward amination of dibenzophenone here. So through these reactions, we can obtain a variety of TAD twisted compounds. So the comparison of the photophysical properties of synthesized DAD compounds revealed that the compound with the largest dihedral angle decouples the electron interactions between the donor and the acceptor units, allowing the small, very, very small delta ESD gap less than 100 milli-electron volt. So another discovery was that the triplet states of the DAD compounds are always localized on the acceptor unit, which is evident from the phosphorescence spectra shown here. So taken together, the merits of using these DAD scaffolds involve the tunability of delta EST gap here, just by adjusting the CT levels to match with the excited triplet state of the acceptor. So, as expected, upon elevating the temperature, the fluorescence from these DAD compounds was boosted, especially the DAD molecule with the narrowest delta ESD gap showed efficient TADF behavior. So most importantly, these molecules serve as efficient organic emitting materials for OLED devices as designed. The external quantum efficiencies of the OLEDs fabricated with this molecule far exceeded the theoretical maximum of those with conventional fluorescent emitters and achieved as high as 60% EQE. Furthermore, appropriate selection of the host materials in OLEDs allows the irradiation of far-red shifted emission in the near IR region ascribed to X-Cyplex formation with a sufficient quantum yield. So what is more, by incorporating the orange TADF emitter into the emission layer of an OLED device with a blue and green TADF emitters, efficient white emission, white light emitting OLED was realized, which might be useful for lighting applications in the near future. So, with nice TADF emitters in hand, we cast a fundamental question to ourselves. Okay, there exist millions of luminophores, but how many aspects of a luminophore do we see? So in the way we look at polyhedrons, a molecule also should have multiple functional aspects that are hidden and difficult to be seen from the point we stand. But if we can induce multiple functions from a single component molecules, they can find new applications. Okay. So to do so, we focus on the mechanochromic luminescence materials. So typically, the prior arts to design mechanochromic materials utilize the difference in packing modes of luminophore in the solid state. So like this. So in contrast, we assume that the conformational fluctuation can significantly perturb the electronic structure of luminophores and thereby can regulate the emission currents depending on conformations rather than molecule stacking or structures without impairing intrinsic TADF properties. So our TADF material involves two electron donors at the edge of the acceptor, where the donors take only planar geometry like this. So we focus on homologous donors of phenothiodine. So due to the larger atomic radius of phenothiodine takes both chair geometry and depending on the position of a substrate on the nitrogen atom, it takes two conformers, and that is quasi-axial and quasi-equatorial conformer. Quasi-axial and quasi-equatorial is shown here. So therefore, If we put two donors into the acceptor, the molecule can take 4 conformers in total, as shown here. So most importantly, as designed, the compound shows distinct emission curve change in response to various external stimuli, such as mechanical force, or heating, and fuming with organic vapors. The crystallography analysis clearly proved that the donor can take both conformers in the solid state. So, furthermore, the validity of the molecular design was demonstrated by the comparison with analogous DAD compounds. The DAD compounds with carbon bridge or without bridge and oxygen bridge did not show significant or change in emission curves, even when various stimulants were applied to the materials. So these results clearly indicate the importance of the sulfur atom in the donor unit for realizing mechanochromic properties. So, as you can see, the X-ray crystallographic analysis confirmed that the phenothiazide donors can take two different geometric orientations against the acceptor unit. So from the comparison of the emission profiles of the solids and the solutions, we can conclude that the distinct emission curve changes in the DAD system is ascribed to the fluctuation of the CT characters in the excited state governed by conformers as shown here. So importantly, the OLED fabricated with the material on displayed efficient orange TADF, preserving the external quantum efficiencies up to 70%. So I would like to emphasize here again that it represents the first example of TADF active multicolor changing mechanochromic luminescence materials ever. So the follow-up investigations of the mechanochromic materials revealed that photophysical properties are highly dependent on which conformers dominate in the solid state. The mechanochromic material can be useful for detecting the pressure change in solution as well. Upon the application of hydrostatic pressure, diluted toluene solution of the DAD compound nicely shows a ratiometric response in luminescence spectra, also like this. Since the UV-based absorption spectra were not affected that much by the pressure change, this unique ratiometric behavior is rationalized by the structural dynamics in the excited state caused by the DL rotation. So under high pressure, the micro viscosity around the molecule increase the restriction of the DL rotation, so suppressing the reverse intersystem crossing through vibronic spin coupling or spin orbit coupling mechanism. So that will be the reason why the CT TADF here emission at around 650 nanometer decreases upon pressurization. So we were then and became interested in the generality of a molecule design for mechanochromic materials and in the effect of electron or donating ability on the photophysics. So we designed and synthesized the DAD molecule with a phosphine sulfide bridge, in which the donor can once again take both chair, but with less electron donating ability. So we developed a synthetic method for the donor from scratch and synthesized it in good yield. The synthesized DAD compound forms microcrystals from the solution of hexane and chloroform, and in the crystal, this molecule takes quasi-axial equatorial conformation and forms tetramer with the inclusion of solvent molecules. It is worth mentioning that the molecule displays distinct multicolor changing in response to various external stimuli, like a phenothiazide molecule. Also, it showed acid-base response to drastically change the emission between visible and near IR region. Most importantly, the conformational effect on photophysics was clearly showcased by single crystal to single crystal transition. So starting from the crystal, that includes the equatorial conformer and chromophore solvent molecules. The evacuation of chromophores and the reduced pressure caused the conformational change of a donor from equatorial to into axial, preserving the intermolecular distances in the crystal. The clear difference in emission profiles between these crystals would once again validate the importance of the conformational fluctuation of the molecules on the emission profiles. So what is more surprising was the effect of electron donating ability on the emission properties. The phosphorus-containing compounds dispersed in non-polar matrix or DELNet showed dual emission comprising of TADF and room temperature phosphorescence RTP. So this makes a significant contrast with the emission of sulfur-containing compound shown here, which showed typical CT type TADF. A probable explanation for the interesting phenomena of the would be the larger delta ESD gap caused by the destabilization of the CT1 excited state suppresses the reverse intersystem crossing from the local triplet state, and thereby the long-lived triplet excited state is depopulated by the irradiation of phosphorescence. So, okay, let me switch the gear, and this is the last topic. As you notice, the dibenzophenone has a unique molecular geometry, what we call U-shaped structure. We were wondering if the PHZ has suitable geometry for making pi-conjugated macrocycles or even an appropriate linkers connect the two bent motifs as shown here. So also we noticed that there were no macrocyclic TADF materials that can work in OLED devices when we started the project, meaning that no one knew the effect of microcyclization of linear DL repeating or TADF unit. So we suspect one of the reasons for the scarcity of macrocyclic TADF emitters would be ascribed to the synthetic challenge to make macrocyclic structures itself comprising of related pi-conjugated fragments. So one of my PhD students has devised and established a robust synthetic method for macrocyclic DAD compound. So this route has a merit to synthesize an open form analog from the common intermediate here. So it is worth mentioning that the macrocycle has a slight flexibility in conformation, and it forms two polymorphs that display different photoluminescence colors as shown here. One polymorph takes the conformer with central symmetry with a dBPHZ unit forms helical structure. And the molecules stack in a stepwise fashion through cross or pi-pi contact at the acceptor unit. The other is more thermodynamically stable or saddle type conformer, where the boss of the dBPHZ core is totally flat. In this case, the molecules are stacked very beautifully to form a column with a molecule size channel or through alternating intermolecular or through space DA interactions. So to investigate the TADF properties of the macrocycle and the effect of macrocyclization of the repeating unit on properties, so we compare the photophysical properties of macrocycles and the linear node. At a glance, the absorption and emission behavior in solutions look alike, but an important message here is the macrocyclic compound showed greater quenching of the photoluminescence under the oxygen atmosphere. This suggests the emission from the macrocycle is more contributed from the triplet related excited state, meaning more TADF contributions in luminescence. So the time result of photophysical analysis of the emitters in polymer matrices gave us the decisive result. as clearly seen at the microsecond region. More distinct delayed emission was observed for the macrocyclic TADF compound than linear compound. Although the singlet or trapped energy splitting is moderate, the OLED fabricated with the macrocycle achieved a high EQE up to 11.6% EQE, exceeding the value using the linear analog. So this clearly demonstrates the efficacy of cyclization of DNA repeating unit for improving TADF functions in the scaffolds of the dibenzophenolene donor system. So, in summary, we have showcased that the discovery of a single reaction provides great opportunities for investigating on new pi-conjugated scaffolds and developing unique multi-functional organic material. So finally, I'd like to thank all the people of the medical laboratory. Especially, I'd like to acknowledge the students who have been engaged in this project. So I would like to thank all the collaborators within the Horizon 2020 project, X-Lite, and Octa project funded by European Commission. So I also thank the financial support from Mexico, Japan, and the third fund agencies. So thank you for your attention.
Thank you, Takeda. Apologies, just the connection issues, but there we go, all back. Right, I believe we have a question. Just looking now. Okay, so we have a question. So from one of our attendees, I'm curious how large the aggregates you presented in the last section can be. How large can they get to?
Yes, sorry. Once again.
Yep. Sorry. So we have a question about how large, in the last section of your talk, how large are can the aggregates that you were talking about? How large can they grow to? Have you looked at that?
So you mean the singlet triplet energy gap?
I'm not sure. This is a question that's been posed.
How large? Sorry. So okay.
Okay, so maybe I'll move on. So we have another question.
Maybe I have one question actually.
Oh, yeah. Okay.
It's fine.
Yeah.
Actually, very interesting talk because actually my research more focus on fundamental researches such as design, synthesis, some new molecular, you definitely more functional purpose. So I'm wondering how about the yield about your dibromo DBPHZ? I'm quite interested in your molecular. You discovered due to the unexpected reaction, right? How about the yield?
Yeah,
with
yield is like okay. So for brom dibenzophenolene is like 50% alone. So not about. Yeah, so it is the problem is it is a little bit insoluble in organic solvents. So sometimes it makes a problem.
Yes, because it's large enough and also low bucket group to input a bit. So you can do large scale for this reaction, such produce gram scale about this dibromo.
Good question. Yeah, we are trying every time to with a large scale, but yeah, if we increase the scale, it is messy. Yeah, but yeah, The problem is
So
the
you
purification.
to
Yeah.
the large scale, the yield will decrease. It means.
More like I would say the purification to the COM will be more problem. So if you increase the scale, yeah. So you need a large COM.
Okay, well, then it's fine. Thank you. Thank you very much.
Yeah. Thank you.
Thank you. So we just have one other question in the chat, Dr. Takeda. So there's a question: have you checked for the presence of long-distance pi-pi interactions in solutions that may cause some of the shifts that you'll do in the spectra that you show?
Okay. So which compound is he talking about? Yeah, we have a lot of pi-conjugated compounds.
In general, we could say, in general, have you looked for the presence of long-distance pi-pi interaction?
Okay, yeah. Yeah, sometimes some molecules they show the concentration dependent behavior of the UV-based and the photoluminescence. So maybe the pi-pi interactions all should be included in the higher concentrations in some cases.
Okay, thank you very much, and thank you once again for your talk.
Thank you.
And, okay, thank you. We'll move on now. Thanks. Okay, so our final speaker today is Dr. Roxanne Kieltyka. Dr. Kieltyka did her PhD, or finished her PhD at McGill University in Canada under the supervision of Professor Dr. Slyman. Post PhD, Dr. Kieltyka did some her postdoctoral research at Eindhoven University of Technology in the Netherlands under the guidance of Professor Meyer. And then since that position, since her postdoctoral position, she has secured a tenure-track assistant professorship at Leiden Institute of Chemistry, also in the Netherlands. Dr. Kieltyka is our early career advisory board member for ChemNanoMat, and tonight we'll be speaking, this afternoon, this morning, depending on where you are, we'll be speaking on Squaramide-Based supramolecular materials from a self-assembly to biological application.
Thanks, Paul.
Thank you. Thank you. You may.
Thanks, Paul, for the kind introduction, and thanks to Claire and Andre for putting together this virtual symposium and the invitation to speak here today. Let me share my screen. Okay. Can you see it?
Not yet.
Not yet?
Not yet.
Okay. And now?
Yes, that's good. Yep, now we can see it. Thank you.
All right. Okay, so today I will share some of our work in developing Squaramide-based supramolecular materials, namely their self-assembly and our first forays into their biological application. One material that inspires much of our work is the natural extracellular matrix. It is the natural biomaterial that all cells reside in. It is a water-rich matrix that consists of proteins that are fibrous, such as collagens and elastins, as well as polysaccharides, and varies in composition with its location within the body. Its function is to provide the necessary biophysical and biochemical cues to drive cellular behavior in processes such as development and disease. In short, this natural material is not only chemically complex, but is highly dynamic, being secreted, remodeled, and degraded by cells. Consequently, there is an interest in the healthcare area in water-rich materials or hydrogels to mimic this natural material for a wide range of applications where cell culture is involved. For example, in the areas of disease modeling, drug screening, and toxicity testing of therapeutic compounds, tissue engineering, and regenerative medicine to replace or repair diseased or injured tissues, and as well in the area of drug delivery. For applications involving 3D cell culture, hydrogel materials based on biopolymers, such as proteins or carbohydrates, are widely used because of their capacity to provide various biological cues and commercial availability. However, chemical modification of such matrices to modify their mechanical properties, the decoupling of cues, their lot-to-lot variability, and their origin can be challenging for their application depending on the target that is aimed for. On the other hand, synthetic polymer materials offer possibilities to fine-tune and decouple various aspects of these matrices with better reproducibility, but it still remains a challenge to engineer cells grown in vitro to be on par with those raised in their native tissues in vivo that are exposed to a complex, dynamic, and involving environment of various biological cues. As a result, there is much recent exploration into matrices and chemistries that enable responsiveness to cells or user-defined changes in materials' properties to mimic some of the dynamic features of the natural extracellular matrix. Of these strategies, we are particularly interested in supramolecular materials, where the monomers are held together by non-covalent interactions, and that's because of their potential to mimic the structure and function of ECM proteins and their responsiveness to their environment. This class of materials also has practical advantages, such as their capacity to undergo self-healing or shear thinning, the possibility to mix and match or multiplex biological cues, and their ability to easily seed and release cells from a three-dimensional environment. So we wanted to prepare a supramolecular polymer material, but we wanted to do it differently. We wanted to use a minimalistic synthon that was also synthetically accessible. As a result, we became interested in the Squaramide, a simple ditopic synthon that has two carbonyl acceptor groups opposite two NH donor groups on a cyclobutene dione ring with partial aromatic character. The Squaramide synthon can be easily introduced into a range of scaffolds through starting from their commercially available squaric diacid esters. They have been examined in the areas of medicinal chemistry, catalysis, the ion receptor field, and more recently in supramolecular polymers. So our first approach to prepare a Squaramide-based supramolecular material that self-assembles in water was performed by Victoria Saez-Talens, a PhD student in my group, who first inserted the Squaramides into the hydrophobic domain of a boloamphophilic monomer that has polyethylene glycol chains on its periphery. He synthesized the bisquaramide boloamphophile over 3 steps with moderate yields of 60 to 70% and then went on to explore its self-assembly behavior in water. As a first approach, he used cryo-electron microscopy to examine the morphology of the formed supramolecular polymers. Through imaging, he found long micron-sized fibrils with a diameter of approximately 6 nanometers. He further went on to explore their morphology through small-angle X-ray scattering in collaboration with Ilya Futz at the Technical University in Eindhoven. In this measurement, what he found was that he found scattering profiles that are consistent with fibrillar objects, and from this data, he was able to determine that there are 11 boloamphophiles in the cross-section of the supramolecular polymer using the experimentally determined volume of the cross-section. This means that the Squaramide-based boloamphophiles not only aggregate parallel to the fibrillar axis, but also laterally. We further examined the effect of self-assembly on the Squaramide synthon by comparing its IR spectra with and without hexafluoroisopropanol, a potent hydrogen bond disrupting solvent and a good solvent for the monomer. We found that polymerization of the Squaramide-based boloamphophiles in D2O results in significant red shifting and increased intensity of the NH and CO stretches within the Squaramide moiety. This result is consistent with hydrogen bonding of the Squaramide units within the polymer in D2O. Additionally, a similar redshift and increased intensity of the ring-breathing peak of the Squaramide was observed. And this red shift indicates a perturbation of the bond length within the Squaramide moiety and suggests that a ring with less bond length alternation is formed upon assembly. These observations were confirmed through DFT calculation. More recently, Joyal Davis, a PhD student in my group, in collaboration with Kartik Gupta at Leiden University, used heteronuclear solid-state NMR experiments to further demonstrate the head-to-tail hydrogen bonding mode of the squaramide synthons. With a longer contact time of 2 milliseconds, cross-peaks between the squaramide carbonyls and the CC double bonds with the nearest protons on the methylene carbons and the amine hydrogens were observed in live lyse samples from water on the right. On the right, these signals were absent in the squaramide monomer dried from a good solvent on the left. We further examined the consequence of self-assembly on the squaramide unit electronically using UV-vis spectroscopy through the titration of a good solvent to the assembly. Self-assembly of the squaramide bowl amphiphile into a supramolecular polymer resulted in simultaneous red and blue shifting of the HOMO-LUMO +1 and HOMO-LUMO transitions of the squaramide with a concomitant increase in intensity. Moreover, we found that DFT calculations predict similar trends in the absorption spectra upon oligomerization of the squaramide unit in a head-to-tail hydrogen bonding arrangement. Experimentally, we observed that geometric and electronic changes to the squaramide synthons occur upon supramolecular polymerization. However, we wanted to further understand the effect of self-assembly on the aromatic character of the squaramide synthon, as it was previously demonstrated by Frontera that the aromaticity of the squaramide synthon increases when it interacts with ions non-covalently. However, aromaticity is not a directly measurable quantity by any single experimental technique. It is a multidimensional phenomenon. To be considered aromatic, cyclic pi-conjugated compounds should show differences in their magnetic, geometric, and energetic features relative to their acyclic analogs. As a result, computational techniques are used to tackle these various indices, such as the nucleus-independent chemical shift method, which estimates a magnetic field at a given point above the center of the ring in question, the harmonic oscillator model of aromaticity, that is a geometric index that measures the degree of bond length alternation within the ring, and the aromatic stabilization energy, which is a thermodynamic parameter that assesses the increased stability due to a gain in aromaticity. So our collaborators, Pablo Nguyen, formerly at the Technical University in Delft, and Tuat Trinh at the Norwegian University of Science and Technology, performed various calculations to better quantify the change in aromatic character with the oligomerization of the squaramide moiety. They found that through ab initio calculations, geometric changes towards bond length equalization within the squaramide moieties occurs on going from a single squaramide to the central squaramide in a pentamer. Above, or in regular case, the monomer, below, in italicized case, the pentamer. Moreover, when applying the Home equation on these DFT optimized geometries, a greater aromatic character was computed on the pentamer than in the monomer. As a reference, fully aromatic compounds like benzene have a value of 1. Using the nucleus-independent chemical shift method, a decrease in the ppm is computed for the squaramide monomers upon oligomerization. This behavior is consistent with an increase in their aromatic character. Finally, we measured the aromatic stabilization energy by comparing oligomerization of the squaramide against a reference compound having the same functional groups but cannot access this effect. We found that the contribution of the aromatic stabilization to the total interaction energy in the squaramide oligomers increases with the oligomer length, with aromatic stabilization accounting for over 30% of the total interaction energy of a squaramide pentamer. We further wanted to compare the squaramide against an isostar that shows the same ditopic hydrogen bonding pattern, but cannot gain an aromaticity. For this, we used ureas. We computed their interaction energy per hydrogen bond upon oligomerization of the squaramide against the urea-based pentamer. We calculated a stronger interaction energy per hydrogen bond for the squaramide relative to that of the urea-based oligomer, with a steeper increase in the interaction energy, namely an 18% change in the urea versus a 30% change in the squaramide on going from a dimer to a pentamer. We then set out to perform a wet experiment, where we synthesized both urea and squaramide-based bowl amphiphiles and then performed static light scattering and cryo-electron microscopy. We find that the squaramide-based bowl amphiphile has an order of magnitude lower critical aggregation concentration as determined by static light scattering than that of the urea-based bowl amphiphile, and this translates to a free energy difference of 5.25 kilojoules per mole. Moreover, representative cryo-EM images show long fibrillar aggregates in the case of the squaramide in comparison to short spherical aggregates for the urea-based monomer. Most likely, the stronger hydrogen bonding interactions and the structural rigidity of the squaramide relative to the urea synthon enable the growth of long supramolecular polymers at lower concentrations of building block. So we tried to form gel phase materials from these monomers using several strategies, but we were unsuccessful. So then we started to explore this monomer scaffold for the formation of supramolecular polymer nanoparticles. We then examined the capacity to modulate the nanoparticle size and shape through modification of the size of the hydrophilic and hydrophobic domains. The most prominent effect on nanoparticle shape was observed in cryo-EM imaging through modulation of the oligoethylene glycol domains. By increasing their length to 36 repeat units, the spherical aggregates with a diameter of 9 nanometers were formed in comparison to 11 repeat units that yielded fibers with an average length of 200 nanometers. Small angle X-ray scattering measurements further supported these morphologies in solution, as evidenced by the differences in the slope of the scattering profiles at low Q. We then applied these supramolecular polymer nanoparticles in vivo in a zebrafish embryo model in collaboration with Alexander Cross and Jeroen Boestman at Leiden University, where we tracked their biodistribution behavior in interaction with a key receptor analogously found in the human liver, stabilin-2. And this receptor is known to sequester spherical nanoparticle cargo. So in order to facilitate their tracking, we first co-assembled the various squaramide monomers that have distinct oligoethylene glycol chain lengths with a fluorescently labeled monomer. We then injected the various assemblies in the zebrafish embryos and evaluated their biodistribution behavior. And this is where we found that the fibrillar assemblies associate with the scavenger endothelial cells found in the caudal vein of the zebrafish. We then further evaluated their circulation in stabilin-2 knockouts. In this experiment, we found that the size and shape of the aggregates is important, as the rod-like and fibrillar aggregates were no longer associated with the caudal vein in these embryos. This study shows the potential to use these squaramide-based scaffolds in vivo, but also the importance of nanoparticles' shape and size on clearance by the stabilin-2 receptor. So coming back to gels again, we were looking for a strategy to obtain gel phase materials with the squaramide synthon. Together with Siqing Tong, a PhD student in my group, we decided to try another monomer geometry to prepare the gelator. We designed a tripodal monomer with a tris 2-aminoethylamine trend core and shorter oligoethylene glycol chains. Siqing synthesized 4 alkyl carbon chain lengths ranging from C8 to C12 within the gelator, and performing this synthesis again similarly to the bull amphiphile in 3 one-pot syntheses with moderate yields ranging to 50 to 70% for the various steps. We then started to explore the self-assembly and capacity of this monomer to form gels. We started out with a gel inversion test of the monomer. We found that even with extensive heating of the monomer, it did not dissolve. So then we turned to sonication of the monomers for 20 minutes, and this yielded gel phase materials for some of them. We found that C8 and C10 yielded gels with distinct critical gelation concentrations, whereas C6 and C12 were either too soluble or insoluble. We further probed the mechanical properties of the C8 and C10 gels. In frequency sweep measurements, we found that these hydrogels are very soft viscoelastic materials with storage moduli of less than 100 pascals. We then evaluated their capacity to self-recover through step strain measurements, where we applied high and low strains to the material cyclically. We find that after the application of high strain and return to low strain, the storage and loss moduli of the materials returns to their original values. To better understand the origin of the observed rheological properties, we imaged the hydrogel nanostructure by cryo-TEM in 2D and 3D by tomography in collaboration with Tom Sharp at the Leiden University Medical Center. We find that in the 2D imaging of the gel phase materials, long micron-sized fibers were observed that are approximately 4.2 nanometers in width. When performing tomography experiments on the gel phase materials, we find that there's a dense 3D network of fibers that is present that most likely gives rise to the observed mechanical properties. Moreover, the cryo-TEM images are further supported by small-angle X-ray scattering measurements in solution, showing scattering profiles consistent with high aspect ratio aggregates of a flexible nature. From the intensity of the cross-section, 1 monomer per nanometer was determined along the fibrillar axis. This indicates that on going from a bole amphiphilic to a tripodal monomer geometry, lateral monomer aggregation is reduced and fiber flexibility is increased. Once we characterized the gel properties, we then went on to apply them for 3D cell culture. These experiments were performed by Qingxian Liu, a PhD student in my group, in collaboration with a group of Valeria Orlova and Christine Mummery at the Leiden University Medical Center. We first prepared the gels in PBS and with sonication, as before, to prepare the gels, and then we used their self-recovering character to seed cells in 3D by pipetting the gels several times with a single cell suspension of cells, more specifically induced pluripotent stem cells. Within the group, we are particularly interested in induced pluripotent stem cells, and that's because of their potential to take the patient in account in diagnosing both disease and its treatment. These stem cells are reprogrammed from somatic cells that are obtained from sources such as skin, blood, or urine, and then differentiated into any desired cell type. Because of their origin, induced pluripotent stem cells are free from the ethical issues that are associated with their embryonic counterparts. So once specialized differentiated cells are obtained, numerous applications can be carried out for these cells, such as disease modeling, drug screening and discovery, toxicity testing, as well as cell therapy to repair or regenerate any human tissue. However, there are still challenges in this area, more specifically the efficiency of these various stages in obtaining these cells, and as well their differentiation, their purity, and as well their maturity. And this is where we are interested in using these cells within our materials. So coming back to the experiment, we seeded the single cell suspension of iPSCs and tracked their formation into spheroid within the gels by bright field microscopy. Within the first 24 hours, we found compact spheroids that grew in size over 72 hours, ranging from 26 to 143 microns. Over this period, few dead cells were formed throughout samples when stained by the nuke green reagent, as shown in the merged bright field and fluorescent image above. Here are 2 time-lapse videos of spheroid formation. The first is from 0 to 24 hours, and the second from 48 to 60 hours. These results show that the supramolecular materials do not interfere with the formation of the cell-cell contacts that are needed to form these typical structures from undifferentiated cells. We subsequently wanted to evaluate if we could release the cells from the supramolecular materials in order to further perform downstream analysis on the cells that were contained within the matrix. More specifically, we wanted to know if they retained their pluripotent or if they retain their pluripotency after the culture period. Pluripotency meaning that the cells have no fixed developmental potential and they can still become any cell type. So we diluted the gels in 50% PBS and performed fluorescence-activated cell sorting after incubating the cells with fluorescent-labeled antibodies that are used to, or fluorescently labeled antibodies such as the TRA160 and SSEA4 markers, and these are markers of pluripotency. We found that in the case of releasing iPSCs from the squaramide materials after 72 hours of culture, maintenance of their pluripotent phenotype was observed with histograms of similar fluorescence intensity for both of these markers in comparison to those that were grown in 2D on tissue culture plastic with vitronectin. Additionally, the percentage of live cells by looking at the gated population were similar between the 2D and 3D conditions. So although the results are positive, namely spheroid formation and maintenance of pluripotency, of the cells to look towards applications of expansion, directed differentiation, or the culture of organoids within these materials, longer culture periods, the incorporation of bioactive cues, and methods to modulate their mechanical properties will be necessary. So moving forward, more recently, we have started to explore introducing bioactivity into these squaramide hydrogels through the use of integrin binding peptides. We have used these materials for the culture of HepG2 spheroids as shown here that are used as models for the liver in toxicity screening. Additionally, we have started to explore covalent polymer materials outfitted with 1,2-dithiolanes that generate a dynamic covalently cross-linked network based on disulfides when irradiated with light for 3D cell culture applications. With this, I would like to thank the great group of people that I have the opportunity to work with over the years and as well I continue to work with. And I would also like to thank my collaborators and the funding sources and the audience for logging into the talk today.
Thank you, Dr. Kieltyka. That was an excellent talk. Thank you very much. Just having a look in the chat. Need to hear any questions at this stage, so perhaps I could start by asking one. So, dealing a lot with your hydrogels with the squaramides with live cells. So, is there an issue with toxicity around the squaramides?
We haven't seen any toxicity so far, and most of the MTs show that they're viable as well as the live dead staining.
Okay. Very good, thank you. So there is a question that's come through. So how long do you think the supramolecular nanoparticles are stable for in vivo in the zebrafish experiments?
How long the particles are stable for? So this was measured over a relatively just over several hours of a time point. So this is not a very long period, but they are already being sequestered by the stabilin 2 receptor from circulation.
Okay, very good. Thank you. So you mentioned and you have what, 3 squaramide kind of interactions per kind of on the chain, from what I could see. Have you considered putting more squaramides into your monomeric unit, or is that quite a difficult thing to achieve?
So it's something that we've considered, but at some point solubility becomes an issue.
Yeah, I thought. Okay.
Yeah.
Thank you. All right, so there doesn't appear to be any more questions at this stage. So thank you very much for your talk, and I'd like to thank all the speakers today for all the talks that we've had. We've had some quite some really good variety and quite some really excellent research that's going on. So thank you all for your talks, and I'll hand over to Claire. She'll probably want to say a few words before we finish up.
I do indeed. I'm just going to open up one more thing I wanted to show you. All right, we'll just share my entire screen then. So first of all, thank you, Paul, for moderating today and for bringing us through this session. Thank you to all of the speakers for these excellent talks. I really enjoyed hearing about everything that you are working on and seeing the latest developments. And finally, thank you to everybody who's working behind the scenes. We have people both on the technical side and the marketing side, organizational side, who've all put a lot of work into making this a success today. So if you enjoyed today's event, be sure to keep an eye out for our upcoming future symposia from our sister journals. We'll put a couple links in the chat to pages with registration links, but I wanted to go ahead and highlight one other session coming up later this month, being organized by Chem Plus Chem, that I think might be particularly interesting for this audience. As you can see on the slide here, the event will feature talks by young talents and their mentors, along with flash talks from the winners of the virtual poster competition of the International Symposium on Macrocyclic and Supramolecular Chemistry. So last but not least, thank you all for coming today. With this, I will close the session, and I hope that we can welcome you again at one of our events in the future.
Thank you, Claire.
Bye, everyone.
Bye-bye.